Hello and welcome to 38th set of problems on complex numbers. This is the last set of problems on complex number, though that does not mean that there will be no more problems on complex numbers. Once we finish all the topics on algebra, we will come back to harder problems. They will be under the slide set of miscellaneous problems. Those will be hard problems, and hard problems usually involve concepts from more than one topic, like you might have seen previous problems where complex numbers is related to trigonometry or binomial theorem, things like that. So we will keep such hard problems for the end. Also, if you are new to the channel, please subscribe to the channel and press the bell icon so that you can get notified about new videos coming on the algebra topic. After complex numbers, we will move on to polynomials and theory of equations. So stay tuned for that. So without further ado, let's get started. We go to slides and we go to algebra, complex numbers. So there are only 8 problems in this. I will recommend that you watch the previous video so that you can get a sense of where we are. Otherwise, it will be very difficult to just watch this video. If you are not watching the entire playlist, then you might get confused that where are we. Also, when I'm reading the problem, please pause the video, and if you cannot solve the problem, only then look at the solution. So without further ado, let's get started. Question 371 says that if n is even, then prove the identity cos 2 pi by 2n plus 1 cos 4 pi by 4 2n plus 1 up to cos 2n pi by 2n plus 1 is equal to minus 1 to the power n minus 2 divided by 2 to the power n. In previous video, we have solved one such problem where cos was replaced by sine. So this is a similar problem and you can solve it like that. That is problem number 370. So you can solve 371 like 370. You can solve 371 like 370. So I have left this problem as an exercise. Question 372 says that prove that if cos alpha plus I sin alpha is the solution of the equation x to the power n plus p1 x to the power n minus 1 and so on up to pn then is equal to 0, then p1 sin alpha plus p2 sin 2 alpha up to pn sin n alpha is equal to 0. p1, p2 and pn are real. So since cos alpha plus I sin alpha is the root of the given equation, we can write k is sum of k is equal to 0 to n pk cos alpha plus I sin alpha into to the power n minus k is equal to 0, where p0 is 1. So we take out cos alpha plus I sin alpha to the power n, and what we have remaining is sigma k is equal to 0 to n pk cos alpha plus I sin alpha whole to the power minus k is equal to 0, which is equivalent to sigma k is equal to 0 to n pk cos k alpha minus I sin k alpha is equal to 0. Now we write the imaginary part and equate it to 0, that is equal to p1 sin alpha plus p2 sin 2 alpha and so on up to pn sin alpha is equal to 0. So if you compare the real part, then it will be p1 cos alpha plus p2 cos 2 alpha plus up to pn cos alpha n is equal to 0. So for imaginary part, we have proven this, the desired result. Question 373 says that prove the identity cube root of cos 2 pi by 7 plus cube root of cos 4 pi by 7 plus cube root of 8 pi by 7 is equal to cube root of half into 5 minus 3 cube root of 7. We observe that in the cos angles, the denominator is pi. So we are looking at 7th root of unity. So we find the 7th root of unity. We take x to the power 7 is equal to 1, which gives us cos 2k pi by 7 plus I sin 2k pi by 7, where k will vary from 0 to 6. Now these roots are of the equation x to the power 6 plus x to the power 5 plus x to the power 4 plus x to the power 3 plus x to the power 2 plus x plus 1 is equal to 0. This equation has come from the fact that x to the power 7 minus 1 is equal to 0, which will be equal to x minus 1 into this equation. So when this equation is there, these will be the roots where k will vary from 1 to 6. For k is equal to 0, we will have the real root x minus 1. Now we let x plus 1 by x is equal to y. So x square plus 1 by x square will become y square minus 2, and x cube plus 1 by x cube will become y cube minus 3y. So we divide the original equation with x cube to get x cube plus 1 by x cube plus x square plus 1 by x square plus x plus 1 by x plus 1 is equal to 0. Now we know that the x1, that is cos 2 pi by 7 plus I sin 2 pi by 7 will be equal to the sixth root's conjugate. So sixth root would be cos 12 pi by 7 I sin 12 pi by 7. Its conjugate would be cos 12 pi by 7 minus I sin 12 pi by 7. So first root will be equal to that, and second root will be equal to conjugate of fifth, and third root will be equal to conjugate of 4. So we can write that xk plus 1 by x to the power k is equal to xk plus xk bar. So when we add a complex number with its conjugate, the imaginary part gets cancelled, and thus we have 2 cos 2k pi by 7. So we can say that the quantity is 2 cos 2 pi by 7, 2 cos 4 pi by 7, 2 cos 6 pi by 7 are the roots of the equation y cube plus y square minus 2y minus 1 is equal to 0. Now we consider the roots of a cubic equation x cube minus ax square plus bx minus c is equal to 0. We let these roots to be alpha plus beta plus gamma. Then we apply Vieta's relations, giving us alpha plus beta plus gamma is equal to a, alpha beta plus beta gamma plus gamma alpha is equal to b, and alpha beta gamma is equal to c from this cubic equation. Now we consider equation whose roots are cube roots of this equation's roots. That is cube root of alpha, cube root of beta, cube root of gamma. Let's consider this equation is x cube minus capital A x square plus b capital Bx minus capital C is equal to 0. Then again from Vieta's relations, cube root of alpha plus cube root of beta plus cube root of gamma will be capital A. Cube root of alpha beta plus cube root of beta gamma plus cube root of gamma alpha will be capital B, and cube root of alpha beta gamma is equal to capital C. But we know that m plus p plus q whole to the power 3 is equal to m to the power 3 plus p to the power 3 plus q to the power 3 into 3m plus p plus q into mp plus mq plus pq minus 3mp cube. So we substitute the roots in this, and we obtain capital A cube is equal to a plus 3ab minus 3c. Capital B cube is equal to b plus 3bca minus 3c square. Excuse me. So in our case, minus a is 1, minus 1, b is minus 2, and c is 1. So capital C is equal to 1. So a cube is equal to 3ab minus 4, and b square is equal to 3ab minus 5. Because c is 1, so this will be minus 3, and b is minus 2, so minus 5. And this should be 3ab, not 3bca. Oh no, c is 1, so it will become 3ab, that's fine. So now multiply these equations, and we put ab is equal to z. We will have z cube minus 9z square plus 27z minus 20 is equal to 0. That is z minus 3 whole cube is equal to 7. So z is equal to 3 minus cube root of 7. But a cube is equal to 3z minus 4. So a will be cube root of 5 minus 3 cube root of 7. And thus we have the desired result. Note that cos 6 pi by 7 is same as cos 8 pi by 7 if you have doubt about that. Question 374 says that prove the identity cube root of cos 2 pi by 9 plus cube root of cos 4 pi by 9 plus cube root of cos 8 pi by 9 is equal to cube root of half into 3 cube root of 9 minus 6. So this equation can be solved by taking the ninth root of unity. Like previous problem, we have taken seventh root of unity. In this problem, you need ninth root of unity. So I left this problem as an exercise for you. Question 375 says that if a is equal to x1 plus x2 omega plus x3 omega square, b is equal to x1 plus x2 omega square plus x3 omega, where omega square are complex roots of unity and x1, x2, x3 are roots of the cubic equation, x cube plus px plus q is equal to 0. Prove that a cube and b cube are the roots of the equation quadratic equation x square plus 27qx minus 27p cube is equal to 0. So from the first monomial a, we have a square is equal to x1 square plus 2x2 x3 plus x3 square plus 2x1 x2 omega plus x2 square plus 2x1 x3 omega square. Similarly, we have this for a to the power 3, and we put 3 alpha is equal to this much and 3 beta is equal to this much. So we will have x1 to the power 3 plus x2 to the power 3 plus x3 to the power 3 is equal to minus px1 cube minus px2 cube minus px3 plus cube. That will be equal to minus 3 cube because x1 plus x2 plus x3 is equal to 0 from beta relations. Also x1, x2, x3 is equal to minus cube. That's why we have a cube is equal to minus 9 cube plus 3 alpha omega plus 3 beta omega square, and b cube is equal to 9 cube plus 3 alpha omega square plus 3 beta omega. So a cube plus b cube will be equal to minus 27 cube, and a cube b cube will be equal to minus 27p cube. So from these two values of a cube b cube and a cube plus b cube, we can form our equation whose roots are a cube and b cube. Question 376 says that solve the equation 5x to the power 4 plus 10x square plus 1 into 5a to the power 4 plus 10a square plus 1 divided by x to the power 4 10x square plus 1 into a to the power 4 10a square plus 5 is equal to ax. So we let fx is equal to f5x to the power 4 plus 10x square plus 1 divided by x to the power 4 plus 10x square plus 5. Then the given equation becomes fx into fa is equal to ax. Now we compute x minus fx, which is equal to x minus 1 to the power 5 divided by x to the power 4 plus 10x square plus 5. Excuse me. And x plus fx is equal to x plus 1 to the power 5 divided by x power 4 plus 10x square plus 5. So we divide this, we get x minus fx divided by x plus fx is equal to x minus 1 by x plus 1 whole to the power 5. Now we let x minus 1 by x plus 1 is equal to y, and a minus 1 by a plus 1 is equal to b. So x minus fx is equal to y to the power 5x plus y to the power 5x fx, and x into 1 minus y to the power 5 is equal to fx into 1 plus y to the power 5. So fx by x is equal to 1 minus y to the power 5 divided by 1 plus y to the power 5. Similarly, fa by a is equal to 1 minus b to the power 5 by 1 plus b to the power 5. So from these two equations, we deduce that 1 minus 5 y to the power 5 divided by 1 plus y to the power 5 is equal to 1 plus b to the power 5 divided by 1 minus b to the power 5. So we can write that y to the power 5 is equal to minus b to the power 5, which is the fifth root of unity. So yk is equal to minus b epsilon to the power k, where epsilon is the fifth root of unity. But x is equal to 1 plus y by 1 minus y. So xk is equal to a plus 1 minus a minus 1 epsilon to the power k divided by a plus 1 plus a minus 1 epsilon to the power k is equal to cos k pi by 5 minus ia sin k pi by 5 divided by a cos k pi by 5 minus I sin k pi by 5. So with this we have deduced our xk. Question 377 says that find the magnitude of the sum s is equal to nc1 minus 3 nc3 plus 3 square nc5 minus 3 to the power 3 nc7 plus so on. So we consider here the complex number minus half plus I square root of 3 by 2 to the power n, which is cos 2n pi by 3 plus I sin 2n pi by 3. So we write this complex number as minus 1 to the power n by 2 to the power n into 1 minus I root 3 to the power n. Now we use the binomial expansion for this, and we have 1 plus nc1 into minus I root 3 plus nc2 minus I root 3 whole square plus nc3 minus I root 3 whole cube. Now we separate out the real and imaginary terms. The real terms become 1 minus 3 into nc2 and so on, and the imaginary terms we also take out square root of 3. We get nc1 minus 3 to the power nc3 plus 3 square nc5 minus 3 to the power 3 into nc7. So from this equation, it is clear that we are not interested in the real part, we are only interested in the imaginary part. This should be multiplied with this also. This is a typing mistake. Minus 1 into 2 to minus 1 to the power n into 2 to the power n will be here also. So our imaginary part on the left hand side is I sine 2 n pi by 3. So our s becomes minus 1 to the power n plus 1 into 2 to the power n divided by root 3 sine 2 n pi by 3. Question 378 says that find the magnitude of the following sum. Sigma is equal to 1 minus nc2 plus nc4 minus nc6 plus and so on. Sigma prime is equal to nc1 minus nc3 plus nc5 minus nc7 plus so on. So we consider here 1 plus I to the power n, and we get 1 plus nc1i plus nc2i square plus nc3i cube and so on. Now we consider 1 plus I in polar form as square root of 2 cos pi by 4 plus I sin pi by 4. So 1 plus I to the power n will become 2 to the power n by 2 cos n pi by 4 plus I sin n pi by 4. Therefore, we can compare the real part and we can write 1 minus nc2 plus nc4 minus nc6 and so on is equal to 2 to the power n by 2 cos n pi by 4. And sigma prime becomes nc1 minus nc3 plus nc5 minus nc7 plus so on is equal to 2 to the power n by 2 sin n pi by 4. Now n can have different values. It can be mod 4, that is, it can be 4m. So the remainder is 0 here. In that case, sigma will be this much and sigma prime will become 0. If n is 4m plus 1, then sigma and sigma prime both will be equal to minus 1 to the power m, 2 to the power 2m. If n is equal to 4m plus 2 and then sigma is equal to 0, and sigma prime will become minus 1 into 2 to the power 2m plus 1. Similarly, if n is equal to 4m plus 3, sigma will become minus 1 to the power 2m plus 1, 2 to the power 2m plus 1, and sigma prime will become minus 1 to the power m, 2 to the power 2m plus 1. So with this, we come to the end of 38th set of problems on complex number. I hope you are enjoying our journey through the class 12 algebra problem solving, and I hope that you will stay together with me till the end of this subject and plus many more subjects to come. So please like the video and share it on social media as much as you can, and make use of the comment box to make suggestions or improvements. And thanks a lot for watching. See you in the next video. Have a nice day.